said, let's take a couple moments and let's calendar together and let me help you understand what what this unit is going to look like in general. Go on from there. So guys, this entire unit hinges around the word therefore. So guys, if you don't understand this, therefore is a relational and an argumentative word. If you want to see brilliant use of the word therefore, read the book of Romans. Paul is an expert at using the word therefore. He ends a chapter, he's making an argument, and then the beginning of the next chapter begins with therefore. And basically what he's telling his reader is, hey, I established an idea. I established a principle or a truth. So what comes as a result of that principle or truth? And it's a therefore. So guys, what you're going to find out is this entire unit that we're going to get into is all about therefores. So guys, let me help you make the jump. So, oh shoot, the heading is gone. Why is it not there? So guys, today on the 12th, and the heading is gone, you are going to learn about molecular polarity. So guys, let me help you make the connection. Do you guys remember in the lab that we did when you had the model kits, what were you writing yes or no down for in the far right-hand column? The symmetry. So guys, that's our first therefore. We are going to ask today this question: is a molecule symmetrical? If the answer is yes, therefore it is nonpolar. If the answer is no, it is therefore polar. So guys, what we're going to do today is we are going to link symmetry with polarity. Then guys, when we get back together on the 18th, our next therefore is going to be this: molecules are polar, therefore they are sticky. And the stickiness we call intermolecular forces. Then guys, when we get together on the 20th, the therefore is going to be molecules are sticky, therefore they are liquids and solids and not gases. And so guys, we are going to get done with those therefores on the 20th. Then guys, after that, everything else we're going to do is labs for the rest of the unit. When we see you on the 24th, we are going to talk about, okay, molecules are sticky and therefore they stick together. Therefore, what happens when they change from solid to liquid to gas? How does the stickiness change? And then guys, we on the 26th are going to wrap up those ideas. Then guys, when I see you on the 30th, we're going to study a thing called colligative properties. And then when I see you on Wednesday, the 1st, which happens to be my birthday, so you can get your shopping in early. Guys, we're going to wrap up that idea, and then Friday the 3rd is going to be the test. So guys, again, the idea is that this is all about therefores. In addition to that, one other thing, guys, I will give you your test back on where are we at here. I'll give you your test back on Wednesday, the 18th. And then guys, remediation is Monday or Tuesday. And then the essentials test is Thursday. So guys, if you have not taken the test yet, you don't need to leave. You're fine. I'm not going to give it back to you today, but make arrangements to take it. Even today after school could be a lovely option. And then you don't have the 4-day weekend to forget the material. So guys, questions about the calendar? Questions about any of that? Okay, so we talked a moment ago about how we're going to approach today's material. Guys, slow me down if you need to ask questions. But guys, we're going to jump into this. And again, you are going to find this material really familiar. We're just going to organize it a little differently. So guys, here we go. This was functionally the last page of the test, kind of. It was spread out a little bit, but you were drawing Lewis dot structures and then you were identifying names and angles. And guys, when we do the test essentials, when I see you next time, what you're going to find out is this. Drawing Lewis dot structures is essential, but giving their names and angles is not. Guys, after you take the test, you can forget all the names and angles. You don't need to worry about them anymore. Those go away. Those are not essential. That's why we gave them to you in matching on the test, because we figured, hey, if they don't need to know them down the road, let's just make it matching. So guys, we'll come back to this in a minute. Then guys, thought number 2 is this, and James, you mentioned this. We've got this idea of symmetry floating around in our head, which means the same in all directions. And then guys, finally, the third thing that we're going to come back to is when we talked about what we called polar covalent bonding. Again, guys, we did it in the last unit. We touched on it very briefly. It wasn't even on the test. And so guys, we're going to touch on these 3 things. Structures of molecules, then we're going to touch on symmetry, then we're going to touch on polar covalent molecules, and then guys, you're going to have the rest of the day to get your homework done. Yeah? Oh, do we have people? Oh, thank you. Hi, Bruce. Sorry. After about 10 minutes, just let yourself in. So you need a sheet of paper, and you're good to go. Guys, again, those are the 3 ideas. Not that, just a sheet of paper. So guys, again, 3 ideas. We've got the idea of Lewis dot structures, but not names and angles, symmetry, polarity. We're good to go. So guys, this then brings us to what we're going to do today. So guys, these are our 3 goals for today. We are going to learn to connect Lewis dot molecular structures with their actual 3D structures. I'll show you what that means. Then we're going to review polar covalent bonding. Then we're going to bring all this together and we're going to talk about polar covalent molecules. And then you're going to get your homework done. So guys, again, there's 3 things that we need to review. Ask questions as we go. So guys, the first thing that we need to do is this. We need to link 3-dimensional structures with Lewis dot structures. So guys, follow along. If you need to jot, but anyway. So guys, it goes like this. So you've already drawn all these Lewis dot structures. I'm going to zoom into them. But guys, you've already drawn all these Lewis dot structures. So let me just show them to you. So guys, first of all, CCl4 looks like this. Talk to the person next to you about its domain, molecular geometries, and angles. And some of you right now are thinking, wait, I thought we didn't need to know these. Just trust me. Guys, what are the names and what are the angles? Chat about it really quick. There you go. Oh, and guys, I didn't have this time this morning to build these, so I'm going to fumble. So guys, again, you don't have to know this, but you need to be able to think about it. So how many domains on the central atom? 4. What's the domain geometry? Tetrahedral. Why is the molecular geometry also tetrahedral? Do you remember? It's all bonding. There are no dots. Guys, please come back to that. If there are no dots on the central atom, the domain and molecular geometries are the same. And then, guys, the angle is 109.5. Is that okay? Okay. So, guys, this is the new idea. This is what it looks like. This is tetrahedral, right? Guys, this is how we will draw tetrahedral. This is as good as we can do on 2-dimensional paper. And guys, this is how we're going to draw tetrahedral. But it gets a little weirder as we move on. So there's our tetrahedral. But now guys, this, carbon dioxide. Carbon dioxide is double-double bonds. Talk to the person next to you about the domain and molecular geometries and angles around the carbon and carbon dioxide. Talk about it. I love that some of you are saying, but. Yeah, good for you, Emily. So guys, let's talk. First of all, this. if you had on the test written the Lewis dot structure for carbon dioxide for this, like this, would you get full credit? Absolutely. Guys, this is a beautiful three-dimensional or a beautiful Lewis dot structure for carbon dioxide, but it's not best. And let's talk about best. Guys, there are two domains on the carbon. So what's the domain geometry? Linear. Now, guys, there's no dots on the carbon. So what's the molecular geometry? Also linear. And the angle is 180. Guys, it looks like this. But here's the problem. If we look at the Lewis dot structure that we have on the screen, it looks bent. And so, guys, this is going to be the additional layer to the onion that you are going to add today. If you draw a Lewis dot structure like this, and you don't even need to know the words, you don't have to be able to say linear, but you need to be able to look at this and have something in your brain that says this is all in the same line, and then you need to redraw it as being linear. So guys, the new layer this day is that we are going to draw our Lewis dot structures as three-dimensionally accurately as we possibly can. And so once we're done drawing the Lewis dot structure, if we realize that we could do a better three-dimensional job, we're just going to redraw it. Is that okay? All right, so guys, let's keep going. So our next molecule is going to be water. Guys, this is a perfectly legitimate Lewis dot structure for water. But we've got 4 domains on the central atom. So what's the domain geometry? Tetrahedral. But now we have dots. And that means the molecular geometry is not the same. So guys, what's the molecular geometry for this? Not straight. Bent. So guys, the idea is this. Remember, the unbonded electrons bend this down. So you don't need to be able to say bent. But what you've got to be able to do is go, oh, these unbonded electrons cause this to do that. And so guys, the molecule actually looks like that. So we're going to draw it in a bent fashion, which might look like that. Starting to get the idea? So guys, what about NH3? NH3 looks like this. Guys, let's just cut to the chase. What does this look like in three-dimensional space? Pyramid. Guys, you don't have to be able to call this trigonal pyramid. That is not the critical bit. But guys, what you've got to be able to do is look at this and go, that unbonded pair of electrons makes this look like a pyramid. So the molecule, and you guys may notice that these are the same diagrams in the test you took. Guys, the molecule looks like this. And as a result, this thing looks like a pyramid. Is that okay? So guys, that's the way these things come together. So let's continue on from there. We've got HCl. This thing is straight, and that's the way we draw straight. Is that okay? Okay. So guys, one more to go. And it's CH2O. And it looks like this. And so guys, looking at this thing, can you just tell me the molecular geometry? Trigonal planar. And guys, we're actually going to redraw it and draw it like this. And you've never seen that before. We are not going to draw, we're going to do our best to draw these three-dimensionally accurately. So we're going to go like this, and we're going to draw these 120. This is the first time you've ever drawn a Lewis dot structure with 120-degree angles. And so we're going to go like this. Is that okay? So guys, thought number 1 then is this. We are going to draw or even redraw Lewis dot structures so they're as three-dimensionally accurate as they possibly can be. Questions on that idea? Okay, so then guys, this, and I know that this is review, but it's been a while. But guys, now we need to talk about what is called polar covalent bonding. So we understand from the last unit that covalent bonding is when two nonmetals get together. They're both strong. They both pull on the electrons, mine, mine, mine. Neither one wins, so they share. So guys, this happens when different nonmetals are close enough in strength that they share, but they're not the same. So they share unequally, and this creates dipoles. And guys, we talked about this in the previous unit, saying we'll get there in the next unit, but that's now. So guys, this is really pretty straightforward. Let me show you what we're talking about. So we've got an oxygen atom and we've got a fluorine atom. Guys, which one is stronger? You remember, which one is strongest? Fluorine. Strongest element on the periodic table. So when these things get together, they go like this. The fluorine goes mine, and the oxygen goes mine, and you end up with a pair of electrons in between these two. But then guys, these nuclei close down on the pair, but that pair of electrons ends up closer to the fluorine. Do you remember that? So guys, what does that do? Well, what's the charge of electrons? Negative. And guys, because this pair of electrons is closer to the fluorine, it makes this what we call the negative dipole, and it makes this what we call the positive dipole. So guys, how do we represent that? And the answer is this. This is a new idea. Guys, what we do is we draw an arrow. And that arrow represents the direction that these electrons are drifting. That's actually the word we use. So guys, what direction will the arrow always point? At the more electronegative atom. So fluorine is stronger than oxygen, so the electrons draw towards the oxygen or towards the fluorine. And then guys, what we do is we cross the other end of the arrow, meaning that this end is positive, and because the electrons drift towards the stronger fluorine, that end is negative, so the arrows point in the direction of electron drift. Yes, ma'am. Bingo. You see how this is all starting to come together? So the idea is that you can predict the direction these are going to flow based upon their electronegativity, which are trends on the periodic table. Don't, however, think this. Don't think that this arrow moving to the right means that that's telling you that the one on the right is stronger. It's not like the arrows that we drew for the trends, because if we had simply flipped these and put the fluorine on the other side, then the arrow would go in the other direction. Do you know what I'm saying? Is that okay? And then guys, of course, you know this, but just to bring this full circle, remember when we draw Lewis dot structures, we don't draw dots, we draw bonds. How are we doing on thought number 2? You guys ready for thought number 3? Guys, it goes like this. And again, you're going to trust me on this, right? So guys, when we talk about molecular polarity, and this is the skill that you need to have today, guys, the way that this works is step number 1 is to draw the Lewis dot structures as realistically as possible. So guys, what do we mean by that? Well, that's what we just looked at. We don't draw water in a line. We draw it bent. We don't draw carbon dioxide bent. We draw it linear. We don't draw CH2O with 90-degree angles. We draw the 120s. So guys, we're going to draw these as realistically as possible. Then the next thing that we're going to do is draw polarity arrows for each one of the bonds. What direction do the arrows point? We just talked about it. They point towards the strongest atom. Then guys, the next thing we're going to do is figure out if the molecule is polar. And as James mentioned, this gets back to symmetry. Symmetry means the same all the way around. So if a molecule is symmetrical or balanced, it is nonpolar, and we will write nonpolar underneath it. Now, if we have a molecule that is imbalanced or non-symmetrical, we're going to use another arrow to represent the overall polarity. So guys, I know this doesn't make a ton of sense to you right now, but after I show you 3 or 4 examples, I think you're going to be good on this. You ready to go? Okay, so guys, let's do this. These I would encourage you to scratch down. So guys, the first thing that we're going to do is CCl4. These are the same molecules and by the way, guys, draw these big, about 2 inches across. Draw them big. Hey. Oh, sure. Actually, don't do that. Here. You're going to need to be able probably to erase. Do that instead. All right, now guys, do this. Grab your periodic tables and flip them over on the back. I should have told you ahead of time to grab them. I just forgot. So guys, grab your periodic tables, flip them over on the back. All right, so guys, do this. Find carbon, find chlorine. Which one's stronger? I frankly don't know the answer. So hold on. So as we go down, they get weaker. As we go to the right, they get stronger. Is chlorine stronger? I don't know. Is that true? I don't even remember the numbers. So the electronegativity of chlorine, yeah, and then, or I'm sorry, carbon. So chlorine's stronger, right? Okay, so guys, here's what you're going to do. With a pencil, you are going to represent the fact that chlorine, don't write this down, you're going to represent the fact that chlorine is stronger, so this pair of electrons is actually moving towards the chlorine. Just a second. So the way you're going to do this is you're going to draw an arrow through the bond pointing at the chlorine and then cross the other end. Yeah. Oh, yeah. Guys are pathetic. Oh, you're going to buy her a donut, aren't you?
I don't need a donut.
You don't need to buy me a donut.
I don't need you to buy me a donut.
That's fair. So guys, did that make sense? Chlorine is stronger, electrons drift in that direction. Then guys, this bond, same thing. Chlorine is stronger, drifts in this direction. Chlorine is stronger, drifts in this direction. Chlorine is stronger, drifts in that direction. So we've now identified the polarity of each one of the bonds. The question then is this: is this molecule symmetrical? Talk to the person next to you. Is this molecule symmetrical? All right, guys, we're voting with thumbs. Symmetrical or not? Yes or no? Come on, Bruce. Hey, there you go. Guys, this molecule is symmetrical. So what does that mean? Guys, check this out. Here's what that means. If you pull this way and this way and this way and this way with the same force, because they're all chlorines, if you pull in all four of those directions with the same force, does the carbon atom move? Would it move if you were pulling on 4 ropes equally in all 4 of those directions? Would the middle of the rope move? No. That's what it means to be symmetrical. So guys, this molecule is symmetrical. For those of you that have taken physics, these are vector sums, but you don't need to understand that. But guys, because these poles are equal, this molecule is nonpolar, and we label it as such. So guys, after this, we are going to get into all of the therefores, and it's going to go like this over the next 3 days. CCl4 is not polar. Therefore, it's not sticky. intermolecular forces. Therefore, it's a gas. So guys, all molecules that are nonpolar, well, not all, there's a couple exceptions. Most molecules that are nonpolar are gases at room temperature. We'll talk about it more. All right, so now guys, next example, carbon dioxide. Oxygen's stronger, right? Would you check? That's just in a row. Yeah, so oxygen's to the right of carbon. It's in a period. So guys, oxygen is stronger than carbon, so I'm going to kick you out of the nest a little bit. Draw your polarity arrows. So guys, drawing in your polarity arrows, do they point in or out? They point out. Oxygen is stronger than carbon, so this, One moment, please. Oh shoot, I clicked too many. There we go. So guys, starting again, oxygen stronger than carbon goes in that direction. Oxygen stronger than carbon goes in this direction. Now, is it symmetrical? Do those poles cancel out? Is it symmetrical? Do the poles cancel out? Guys, if you pull equally in both of these directions, does the carbon move? No. That means it's non-polar, so we're going to label this as non-polar. And then, guys, you ready for some earth-shattering news? Carbon dioxide's a gas. Huh. But now you know why. Guys, carbon dioxide is a gas because it's symmetrical and therefore non-polar and therefore not sticky and therefore it's a gas. Go ahead.
I was gonna ask when it's the double bond, you only draw one arrow?
Yes, yeah, because it's the entire bond. Nora, should you come back for AP next year, we talk about the differences between single, double, and triple bonds. And what you find out is they do take up a little more space, but importantly, they are shorter and they're stronger. But these are both double bonds, and so they're shorter and stronger equally. So we just need one arrow. You guys good? Let's play with another one. Guys, please don't write this down because I'm setting you up a little bit, but let's, still drawing dots. Please let me switch. Not going to let me switch. Guys, this is going to freak out for a moment. Hang on. All right, so guys, let's take a look at water. Please don't write it. So guys, is this a correct Lewis dot structure for water? Yes, but it's not best. Because guys, 4 domains, 2 are bonding. All you got to remember, guys, is that the unbonded electrons make these things bend. So what's a better way to draw this molecule? Like this. So if it's bent, draw it bent. So go ahead and draw it. So now, guys, looking up the electronegativities, these I know. Hydrogen is 2.2, oxygen is 3.44. Oxygen's stronger. And so, guys, the idea then becomes that this arrow goes like this, and this arrow goes like this. But now, guys, check this out. Is this molecule symmetrical? It's not. So now, guys, what we've got to do, watch and think about how this goes. We have to draw in the overall symmetry or the overall polarity of the molecule. So, guys, this is the idea. We have an arrow that is going to the left, and we have an arrow that is going up. So, guys, what is the sum of left and up? Diagonal, left and up. So guys, the sum of these is diagonal left and up. And you draw it through the middle of the molecule. So guys, what this means, ready, is water is a polar molecule. The oxygen end is the negative dipole, the hydrogen side is the positive dipole, and this molecule is polar, therefore it's sticky, ready for the earth-shattering stuff. Therefore, water is a liquid. And guys, this is literally what happens. These water molecules work like little magnets, and the negative dipoles and the positive dipoles attract each other, and they stick together as a liquid. That's all the therefores that we're going to talk about down the road. So guys, we're going to do 2 more, and we're going to turn you loose on the homework. So it goes like this. Guys, our next one is NH3. So let's just do it. Nitrogen is stronger than hydrogen. Nitrogen is stronger than hydrogen. Nitrogen is stronger than hydrogen. Now guys, do those 3 poles cancel out? They do not. It's not symmetrical. So now we've got to figure out what the sum of in and up are. And what does in and up add up to? Up. So guys, we draw a big old arrow like this and we cross it. And now we have again the life-changing understanding that this molecule, which is ammonia, is a liquid. Guys, we got one more to do. And it's this, HCl. So guys, we draw in the polarity arrow for the bond. Chlorine is stronger than hydrogen, so that would be the polarity of the bond. But guess what? It's also the polarity of the molecule because it only has one bond. And that's it. So guys, thoughts, things you want to clarify? You guys okay? We just bought you 45 minutes to get your homework done. Guys, you should have the opportunity to get most of this done before the end of the class period. Let me stop my recording and then I'll get these in your hands.